Hi, welcome back. In this lecture, I would like to introduce the graphics processing units, or GPUs, that are devices that are becoming more and more important in high-performance computing application. By the end of this lecture, you will be able to describe the main features of GPUs, how they look like and how to program them. And then you will be able to list the main differences between GPUs and CPUs. And finally, you will be able to list the main approaches for programming GPUs. But let's see what is a GPU. So graphics processing units, in short GPUs, are widely and extensively used in high-performance computing application, specifically to speed up arithmetic-heavy computational workloads. GPUs were originally designed for 3D graphics and specifically for embarrassingly parallel problems, so they do not require strong synchronization or communication across threads. A typical example of an embarrassingly parallel problem is, for instance, to update the value of a pixel in an image. Right? So we can update this value without knowing the information from our pixel most of the time. It might surprise you, but the GPU themselves are typically slower than most of the CPUs. So why is that? Well, the GPU's clock frequency are typically lower than CPU clock frequency, typically half of the value. So if CPU typically run today is around 3 gigahertz, you might find the GPU around 2 gigahertz, 1.5 gigahertz. But why GPUs are actually faster? Well, GPUs are typically faster in certain kind of problem than CPU because they provide a huge amount of parallelism. So they have a staggering number of computer cores. So easily a GPU has thousands or 10,000 cores on a chip. This is almost like to have a personal supercomputer available to you. So 10,000 cores available on the GPU. There are two kinds of GPU. The first one is integrated, and it's the one that you are likely using now that you are looking at this lecture. So these integrated GPUs have a laptop as one and is built into the processor. So you might check which integrated GPU you have in your laptop. You will find out that likely is something like Intel HD or Iris Graphics, but something that is right away integrated on the CPU. The most important for HPC application that we want to use is the so-called dedicated GPU. This is a standalone GPU that is its own processor and its own memory. In the case of integrated, the integrated GPU share the memory. In the case of dedicated, the GPU itself has its own memory. So most dedicated GPUs are removable. So you see here you can actually plug directly on your motherboard. So you can plug and also remove. They require more power. So you see also they require quite a power. Also they dissipate some power. So you see here the fan on the top of the GPUs. But they also obviously provide a higher performance. It's very likely that you heard about the two main companies that are selling GPUs. Probably the most important one when it comes to part of the market that they have on the external GPU is NVIDIA. And also you might heard now about AMD GPU. So AMD are very famous for the CPU, but nowadays also they produce external GPUs. So let's look at an example of what are the differences between CPU and GPU. On the left here I have the number for the clock cycle and number of cores for AMD, and on the right I have a simple NVIDIA GPU called NVIDIA RTX 2080 Ti. As you can see, the clock cycle for the CPU is typically around 3 GHz. In the case of the GPU, is in this particular case is 1.35. So roughly half of the clock cycle. So technically is much slower. The major difference though is really the number of cores. So in this particular CPU, we have 8 cores. In the case of the GPU, we have 4,352 simple cores. So why I make the difference between simple cores of the GPU and the cores, also we can call it the big cores of the CPU. Well, the difference between this simple cores and the CPU cores, these big cores, is that are typically much more simple. They have way less control units, some control part of the chip that is actually removed, for instance, for branching, and also the caches is inexistent or very minimal. Obviously, the architecture are now evolving, so the simple and big cores are becoming more similar. But for the GPU, you can have many because they're simple. They have a less logic, for instance, for the control part. And also when it comes to the caches. So two main differences. One is the clock cycle, and the other main difference is the number of cores that you have between CPU and GPU. So what are the disadvantages? So far, I told you about the advantages. They have a huge amount of cores that you can use for computation. Well, the major issue here is how we move data from and to the GPU. It turns out that many of the drawbacks of using a GPU come from the bus that is connecting the CPU and the GPU. As we saw in the previous pictures, the external GPU is nothing else than a peripheral device, and it communicates through the PCI bus. And this PCI bus is much lower than the front side bus. As a result, getting data into and out of the GPU can be quite a demanding operation. How do we program GPUs? So programming these GPU devices can be sometimes quite difficult, and it tends to be quite low levels. There are certain programming systems that are today dominant, so very popular when programming GPUs. Probably the most important one and most famous is CUDA, that is nothing else than an extension of the C programming language for programming only NVIDIA GPU. This means that if you're trying to program with CUDA and AMD GPU, this is not going to work. So CUDA is a proprietary of NVIDIA. So AMD GPU, they have their own CUDA-like programming approach that is called a heap. There is also a quite famous programming approach, program all different kinds of GPUs and accelerators, called OpenCL. Finally, we have pragma compiler-based approaches that allow us basically to annotate our code, the part of the code that we want to run on the GPU, and the compiler will do the job for us to translate it for a GPU. So you might have heard about OpenMP5 and OpenEC. So in this course, we are dealing with the Python. So how will you do that? Well, there are some approaches. There are many approaches that allow us to write native GPU code, also called kernels in Python. Among the most important approaches, there is CuPy. However, an interesting part of the new developments in machine learning and deep learning algorithms is that there is a new push for new interfaces to program GPU in a simplified way. So it turns out that TensorFlow and PyTorch are the two front runners in easy-to-use GPUs mathematics libraries. So this is the last lecture on my lecture. To summarize the lecture, GPUs are specialized hardware initially designed for graphics application, but today widely used in high-performance computing, and that's why we deal with this topic in this course. GPUs can be either integrated into the processor, like in your laptop processor, or have a dedicated chip. In HPC, we focus on programming dedicated external GPU that can be plugged on the bus, on the PCI Express. So major GPU vendors are NVIDIA and AMD. The major drawback of the GPU is that moving data from GPU memory to CPU memory and vice versa is relatively slow, which might impact how to program the GPU. So we want to minimize the data that is communicated to the GPU. The dominant programming approaches are CUDA, heap, OpenCL, and OpenMP/OpenACC. The easiest approach in Python to program a GPU is to rely on deep learning, machine learning frameworks like PyTorch and TensorFlow. But also there are new approaches that are similar to NumPys, such as called CuPy. So this is the last slide, and talk to you soon.